Okay, let me start. I think I came across a recent paper of yours and Richard Craster, and perhaps in physical review letters. Have you done something similar recently?
No, I don't think so.
Okay.
Nothing on PRL, basically.
Okay. Regarding this, so you're saying that you apply the Floquet-Bloch theorem. Can you repeat this again? So, in fact, your block momentum, it's in the azimuthal direction.
I mean, the idea for me is you have the Helmholtz equation, and then if you express the pressure field in polar coordinates, like a summation of the usual monopole, dipole, quadrupole modes, for each mode you obtain this differential operator. And if you want to, as far as I know, if you want to apply the Bloch theorem, this differential operator should be invariant upon translations in the radial direction, basically. This cannot be made possible if you only have a scalar Bike modulus and a scalar density, because you kind of have these three coefficients that cannot be made at the same time, let's say periodic in the radial direction, if you only have 2 degrees of freedom, which is RB and Rho. So what we learned from this work is that if you assume to have an anisotropic density, so you have radial and tangential inertia, the equation is changed into this one, such that you can independently make this term, and this term periodic. And so then your P solution can be in the form of a Bloch wave. And then what you do is you apply the plane wave expansion method and you obtain a linear system that can, the eigenvalue problem to plot the dispersion. And you see here, for example, maybe I have some backup slides. Let me show. For example, this one is the monopole. I mean, you have this dispersion relationship. The blue curve is just the monopole, let's say. Okay. The light blue curve is the dipole, the one, and you have band gaps, for example. And you can test this numerically by simply sending a signal and do the Fourier transform, basically, to check numerically your predictions. And what happens is that you get something like this, basically, in the radial direction. And one interesting thing I found is that, for example, this monopole mode does not have any cylindrical spreading. The amplitude, it seems to be constant in space. And then it also for dipoles, for example, and you get, for example, the band gap that I showed you. But this is just the, let's so-called radial sonic crystal, as we learned from this paper. And what we thought is, I mean, we were kind of introduced into non-reciprocal wave propagation as a group a couple of years ago by Professor Ruzzene, who works on this stuff, the beams with modulation in space. So I have my colleagues, Jacopo Marconi and Riva Emanuele, who did this beam with piezo pen, in which the idea is just you have kind of pretending to have a moving medium while the medium is not moving at all, because it's just the properties that are changed in time. And so my idea is, of course, this in 1D is highly directional. So you have only one direction and this is it. And if you apply a similar behavior in 2D, let's say you have a wave, the material properties, which is kind of a wave that travels in one direction, the non-reciprocity in this case is still directional because you have only one direction. The bias is only in one direction. Instead, if you want kind of a omnidirectional non-reciprocity, you can imagine the material properties to move in time like divergent or convergent waves. And in this case, you give the same bias isotropically in all directions. So if you see here, this is the radial density, for example, it is kind of in some way modulated in space. It's not periodic because the term which should be periodic is the reciprocal of R multiplied by R according to this, basically. But the idea is, in the end, you have a scaling factor for the curvilinear coordinates, basically. And this is not periodic, but is modulated in space. But this is also periodic in time. So you see that kind of a slope in this space-time diagram. And then, of course, this time variation induces these band gaps to open that are directional. And you get this behavior. For example, is you see radius and time and exciting in the middle, you have waves that goes mostly outside with respect to inside. And the idea is possibly in a future application, one can use this to make, maybe to hear what comes from outside, but not to be heard when you speak, basically, with this non-reciprocal wave propagation.
I've got a question regarding your band diagram. So okay, we are used to these tilted band diagrams for space-time metamaterials, but here in B, it looks like it doesn't go to the origin. Yeah,
you have for all modes higher than the monopole, you kind of have a band gap in the low frequency regime, basically a band gap for frequencies going to 0. And
so essentially
maybe it's kind of a waveguide in which the higher order modes don't have the let's say, do not start from the origin. It's kind of having a radial waveguide in the end. We just only have one dimension, which is the radial one, and the other one is expressed with the modes, basically.
I'm sorry, I'm a bit confused. Your complete band diagram, it consists of the 3 colors, no? Dark blue, light blue, and gray. The complete band diagram.
I get a band diagram, let's say, for each value of Q, basically. So
I agree, but your complete spectrum,
yeah,
you have to take all of them, no?
Yeah, yeah.
Okay, so in the end, you don't have a zero frequency.
No, it's just for some modes.
Yeah. Okay, all right. And so when you go back, yeah.
When I go back here, we are just an excitation that is that has the same symmetry of the mode we want to excite. For example, we can give an initial pressure or a pressure excitation which is constant along a circle to excite the monopole alone, or a dipole excitation basically to excite only the dipole, basically. And indeed, you see, if you do the Fourier transform, basically the 2D space time transform, basically, and these are the results. In this case, you just get the branches for the monopole, and in this case, you get the branches associated to the dipole, basically. While the light gray one is the computations done with the plane wave expansion method.
Yeah, you can clearly see the non-reciprocity the tilt. Yeah, no, it's great. It's great. I have another question. Then, I mean, no, please, people, ask your questions. I mean, enough of me. I mean, you can ask questions on any part of this presentation, which is absolutely fantastic.
I have a quick question.
Yes.
Thank you, Davide, for the very nice talk and impressive results. If you can go back to your slide 13, in the case of, you spoke about the single mode resonance, and the fact that, or 12, this one. And the fact that in this case of the single mode resonance, you have a behavior like the clock starts to behave like a liquid. I mean, propagation is for which polarization, and if you can explain a bit more about this behavior.
Yep, I mean, I can use, so I can maybe draw on, so let's see if this works. usually when you have a pentamode material, you can kind of look at the dispersion, and you have, let's say, something like this in 2D, where you have the longitudinal mode and the transverse mode, basically. And what I learned is that basically, because of the great separation of the bike modulus with respect to the shear modulus, the shear mode gets to a Bragg bandgap, while the wavelength of the longitudinal mode is so big that it is still in the linear regime, or more or less. So what happens is that in this frequency range, you are expecting only longitudinal waves propagating, and this kind of is the same behavior of a fluid, which only can sustain propagating longitudinal waves. So the idea is each one of these unit cells has a different dispersion relation, but in the end, we computed that all of them have a common single mode bandgap. So there should be a frequency range in which only longitudinal waves can propagate inside this one. And a priori, I was convinced that in this frequency range, I would have obtained the best of the results in terms of cloaking, because that is the frequency range in which the pentamode behavior happens dynamically. But it turns out, I don't know if it's just chance. So my configuration, or we need to explore this more. But the idea is that this frequency range, more or less, is the one in which I have the common bandgap for all. And you see the scattered field as a maximum, basically, instead of a minimum in some sense. And the only way I can explain this is that actually, when I look at the dispersion relation, the real dispersion relation, I'm thinking of an infinite material. But this is a finite size specimen. So the evanescent waves take a role, and especially at the interface with the fluid, because the fluid, the pressure well comes, and what happens is that mathematically the field outside should match on the boundary the field inside. And if the longitudinal mode alone cannot, let's say, match the field outside, you should have also the infinite evanescent waves that create kind of boundary layer, the evanescent boundary layers. And in the same way outside, you get maybe a scattered pressure that helps, in some sense, the equations to fulfill the boundary conditions. So maybe, I mean, we all know that in case you have a full bandgap, you have a mirror, maybe having a partial bandgap also induces a kind of mirror effect for some frequency that, I mean, you just not simply have to look at the real bandgaps when you have finite size specimen. But I mean, I honestly have to look more into this. I have tried in these months just maybe to write explicitly this problem of transmission and reflection from pentamodes, but I'm still struggling. Although, I mean, I would expect a transition region, because at high frequency, obviously, the clock does not work because the long wavelength optimization does not work anymore. At low frequency, it works. So I'm expecting a transition. But what is interesting is that the transition happens with a peak and that comes back. And this is strange and could be interesting if I can prove that it is not by chance, only my special case, and it has a reason behind, which can be related to the boundary, the evanescent boundary layer, probably. This is my explanation by now, but I'm kind of open to suggestions if you have other ideas, basically.
No, it's very nice. Okay, thanks. It's clear for me.
There's someone in the chat, maybe.
So thank you very much, Davide. That was a really, really beautiful lecture. I fully agree. Actually, I would like to go back to your optimization formalism, Davide. Right. So, of course, you have some assumption on the regularity of the coefficient A. So A, you said, can be piecewise constant. So A can what is the kind of class of coefficient A that works?
I mean, this should be a question maybe Carlo and Sebastiano can answer better, because they introduced me basically to this optimization stuff. So in the end, this formalism is can work with continuous function because we are retaining the partial differential equations. Basically.
Yeah, but the coefficient A, what is the regularity on the coefficient A? The coefficient A, it's piecewise constant.
In our case, it is piecewise constant.
Yeah.
I mean, you define A as a function of U and V basically, and U and V are just defined as, you see, a summation of indicator functions that has the one inside the hexagon and 0 outside, and then each one is multiplied by a constant coefficient. So then the variables just become the constant coefficient. And we tested several more than this one. Let's say we also had square lattices or a kind of circular rectangular lattices like the cloak, the usual cloak. But in the end, and they all performed well. But in the end, since you have a isotropic material, if you want to implement it in 2D, the symmetry you must follow is the hexagonal one in the end. So the idea was not to choose a whatever continuous function or a whatever discretization, but to just choose this discretization such that in the end, you are kind of including the stage of discretization inside the formulation. Because always you find optimal distributions and then get suboptimal solution by discretizing them. So if from the beginning we include the discretization in the problem, what happens is the solution we obtain is the optimal considering that discretization. And so this was a step. And then of course we also added the constraints on the actual microstructure. And the idea was, can we build a cloak in which we just use unit cells that depend on two parameters. You see here, you have the circular cylinder, you have two parameters, and you can all the possible geometrical configuration in a simple 2D graph. Same for this star-shaped unit cell. Of course, the parameters are more than two. For example, you can add or can change the number of stars. For example, you see 3 stars, 6 points, 6 of these folds, 9 and 12. But we kind of just stick to the 2/3 pi rotational symmetry to have isotropy. But in the end, you can represent everything on a 2D plane, which for us, at least for me, was very good, because you see in this kind of setting, you have a lot of parameters. And visualizing the fact of I change a parameter, what changes in the equivalent property is kind of very difficult. And I mean, as an engineer, I kind of always want to visualize. I mean, if I change this, what changes? It becomes stiffer or denser. And for this, it's kind of, intuitively, I can see that if I can increase this mass, I'm increasing density. But then seeing a graph with 12, 13 parameters is impossible. While in that case, you get a very simple specification, and it's always all very straightforward. And just in principle, we can obtain this with 3D printing. It's just an extrusion of circular or star-shaped inclusions.
I've got another question. So regarding the active cloaking, how do you set up your optimization algorithm? Because now you have sources, and so the sources, what exactly do you specify for them?
So you have the cost functional, and in this case you are considering also time. So you are considering also an integral in time. other than the space, and you have the heat equation basically with its boundary conditions, and you have two sources basically. One is S, which is the external source you want to cloak basically, and one is U, is a distribution of sources which you put around the obstacle. And in the end, what happens is that you want to minimize the difference between the temperature you obtain and the reference pressure, the reference temperature field in time, and while putting a cost also on your expense on the let's say source. And I mean, we did several tests. For example, this was just funny because of the shape, that it's kind of related in some way to the city of Milan. But the idea is we also did, and the control is distributed here. So you have a continuous sources around, like a continuous cloak made of point sources.
But wait a minute, is it a meta surface or are these point sources?
These are active sources.
Yeah, but okay.
Point surface.
But what is their support? Their support is a point, or it's a line, or what is the sources? The support.
It's a surface basically.
So you have a surface.
Yes, a contour. I mean, a 2D contour around the cloak. The obstacle, but also, I mean, I don't have here.
And is it uniform, or I guess this is heterogeneous? I mean, the temperature.
It is heterogeneous, but we also, if you look at the paper, we also made point sources. I mean, not the continuous one, but just one source here, one source, like the active acoustic cloaking in some sense with sources, but the thermal one, and it works also with point sources placed here and there.
How many sources do you need at least? How many?
I mean, I think we tested only the circular object, and I mean, there was kind of 6 or 9, something like that. I should see it on the paper. But,
we've got an archive, because we did the case. I mean, we have a different method. It's using Green's identities, but we did an analysis in the Fourier space. So we use some Helmholtz equation, but with complex wave numbers. And this allows, I mean, we have a maximum principle for this kind of stuff. And so, in fact, we managed to cloak a region with only 4 sources. But apparently, the minimum number of sources would be 1. You could cloak. Also, I think it's very hard to achieve, but it looks like people could achieve, maybe perhaps not for a very complex shape, because but perhaps you could achieve with one source. Perhaps 1 point. Interesting. So perhaps in your optimization algorithm, this can be.
We can check what the minimum number.
Yeah, if this can be, or if this fails. I mean, but 2 sources definitely. 2 sources you can, but apparently 1 source might be enough to cloak.
Yeah, maybe the 2 sources, one is a sink and the other one is a source in some way to take the heat and behind.
Yeah, but in the static case, Onofre, he has a theorem, and it's apparently manages to cloak with 1 source. And also another question, which is very important: your source, it changes with time, or okay. At every time step, you reevaluate.
In principle, yes, you can do.
Yeah. Wow. And okay, I have a very last. What kind of boundary condition do you have? Is it insulating on your animal?
The obstacle is a fixed temperature obstacle.
But it's 0. What you fix it to? What a constant?
a constant, basically.
Okay, a constant. And also, it's very hard for me to see how close are you from the boundary? Can you be extremely close to the boundary of the...
Yes, you see the region you see here, the region of the cloak is this one, basically.
And can you achieve this kind of cloaking, you know, almost supposing dressing the object?
Sorry?
Okay. Could you achieve the same kind of cloaking, but really following exactly the shape of the...
Yeah, I think so. It just was hard to draw the exact. I mean,
okay, that's not...
This is just the...
So, in fact, you don't need to have a convex shape for you.
No, not necessarily. You can see it also here. Convex shape.
Yeah.
In this case, it's the acoustic cloak problem. But I mean, in this case, we have a concave obstacle with the concave cloak, and it works. I mean, this gives also you the flexibility of having a cloak that does not follow the same shape. I mean, if you want the cloak to have the same shape of the obstacle, you can, but you can even do another one in principle. Maybe it can be interesting.
And a very last question. What happens to your algorithm when you have a cloak which is extremely thin, almost a meta surface? So when your thickness is very thin, your algorithm still converges?
Yeah, I mean, what we did in this case was to check for the thickness of the cloak.
Yeah.
And you see, as I said, in this type of simulations, we kept fixed the dimension of the unit cell. So as long as you increase the thickness of the cloak, you have more degree of freedom, and it is easier for the algorithm to find an optimum, which is also better. In this case, you see with 6 unit cells, the performances are just poor, and it takes a lot of time to converge. But if you have a lot of degrees of freedom, then the performances are good. The blue one, it's just a scattered pressure, basically, and also the number of iterations drops. So this is an analysis we did, keeping fixed the size of the unit cells and increasing the thickness. But I mean, if you can keep fixed the thickness and decrease the size of the unit cell, I think you can do a very thin cloak with a lot of degrees of freedom, and then can work in the end, basically. And
in fact, my question is, can you have a cloak which is deeply subwavelength? That's what
we should check. I mean, we have not checked,
because clearly you are even more in the homogenization regime, because
yeah,
you're unique. But
I mean, I have not looked into that yet, but because the primary purpose was to consider also the microstructure, let's say, feasibility constraints. So
yeah,
below a certain size, we did not.
The anisotropy is huge. Yeah.
So, but in the end, if we can pretend we can manufacture everything, we can just do a very tiny cloak, I think, with a lot of unit cells. And it should work, in my opinion. But
I mean, when we reduce the thickness, we increase the anisotropy, no? I mean, when the two boundaries come close to each other,
maybe you increase the anisotropy, which is required if you look at the problem in terms of transformation acoustics. But in this case, we just do not know what is happening in some sense.
Yeah, but somehow.
You are confident that yeah.
I don't know. It doesn't. I mean, you say that your approach is broadband, no?
No, it's broadband if you add the. I mean, in principle.
I mean, here you see you have a 30% of bandwidth, apparently.
Yeah, but in that case, I have introduced more terms in the cost functional. a term for each frequency. So, for example, the 30% bandwidth is obtained when I have the violet curve. So I have 3 targets, one at the central frequency plus 2 besides. So if you want, this is logarithmic scale. So we just picked the kind of the half power, something like that, I think, to set the bandwidth. In that case, you can have a big aperture. But in principle, we do not know what is happening. If the rays are bending around or just it's some scattering, because
so you don't know if it is some kind of scattering cancellation technique.
Maybe it is because it's algorithm that decides all in all. All in all, if you look at this one, it looks a lot like the scattering transformation technique in some sense, but it is not designed having scatterers. It is designed having a finite sized regions of constant materials, basically. So it might be that if the wavelength is big, the wavelength sees it as a gradient, and maybe it bends rays like in the transformation acoustics, or it might be that the wave sees kind of obstacles, hexagonal obstacles, and it's similar to the scattering cancellation. But in principle, we don't know. It's the algorithm that decides the best option for the case at hand. And so if you only consider one case, it will work also only for that case, which is the case here, the blue curve, when we have only one target. And as soon as you move, the scattering increases a lot. If you use, let's say, 2 targets, you have 2 minima basically. And if you have 3 targets, maybe you can kind of have this broadband 30% of the central frequency behavior.
If you would take more points, you would increase further, or 30% is, you think you can increase this bandwidth even further?
Yeah, maybe with some fluctuations in between. But of course, if you increase, maybe this
is not an upper limit. You don't know how it can go.
No, I mean, I'm assuming that increasing the objectives, the performance at each single objective can be worse than the performance you get having only one. As you can see here, when you have one single objective, the performance are the best overall that you can obtain. If you have 3 objectives, the one is less good because it has to take care also of the other. So increasing, maybe you can have a higher performance, mean performance, but putting down the something which is far from the central frequency.
Lovely. So do we have any more questions in the chat box? Apart from Zinon, who was really happy about the talk. I mean, it's a unique opportunity to ask questions to an expert in this optimization technique. So please come forward with your questions. As you can see me, I'm asking very trivial questions, so do not hesitate. I have thousands of questions, but I will have another opportunity to ask some in a month or so. I mean, okay, another silly question. So in terms of computational power, so, you know, to come up with this design, so what was your, computational power? I mean, was it just on a laptop or on
Definitely not. I have a workstation to do this. Especially the anisotropic one.
Okay.
If you don't have the workstation, I don't think you can do this. Especially the step of building the numerical model, the whole numerical model requires a lot of memory because of the complex geometry, and also these unit cells were optimized using an evolutionary algorithm. so the genetic
algorithm. Okay.
Because there's a lot of parameters, and so this in principle can give you, as far as I know, a chance to not be stuck into a local minimum, because it searches in principle the place. Maybe you end up in the local minimum anyway, but it searches. And of course, it was more than 100 unit cells to optimize, because it is not axisymmetric. And so you might think the genetic algorithm is not very efficient for this kind of task. But in the end, if you look at this density distribution, the most of the gradient is in the radial direction and not in the tangential one. So we can set a hard optimization, let me say, only for the first, let's say, column of unit cells. And once we have this one, the optimizing the one in the same, let's say, layer is just picking the first one and asking the algorithm to not to change a lot the parameters, except those ones that control the density. And then
so how did you map your Cartesian system onto the corona? You use a conformal mapping.
Yeah, this is because I mean, when you optimize, you take into account its own anisotropy in XY directions, but then you want that anisotropy to be aligned to the, let's say, ellipse, basically. And I mean, this is not a trivial step, all in all. And it turns out that with the elliptic coordinate system is quite easy, because the scaling factor of the coordinate system are equal. So if you look at this coordinate system, you look at infinitesimal elements, they all have the same aspect ratio, which is something that does not happen in polar coordinates. In polar coordinates, as far as you go from the origin, the thinner they become the infinitesimal element in terms of dr d theta. And this does not happen here. You have equal scaling factor. So it turns out where it is that if you linearly map the Cartesian coordinates onto the elliptical coordinates, it naturally aligns with coordinate lines, and it naturally is an isotropic stretch, so a conformal map, because of this property. While instead, if you do this in polar coordinates, you should take care of the fact that you cannot linearly map x and y to r and theta, because the unit cell will be stretched in the tangential direction as far as you go from the origin.
I totally agree. We did something similar with Luca Pomo, and effectively we needed to use the conformal mapping that kind of effectively was stretching, and really stretching a lot. So our unit cell on the inner boundary was almost infinitely long.
Yep.
Yeah, and I was really amazed to see that that's not the case for you. So it's due to the
fact that the scaling factor are equal. So if, for example, if you want an element which is long Lx and Ly, and you have an element in the elliptical system which is long L theta and L, just Lr is equal to, is proportional to dr, the increment in the coordinate. The L theta is just proportional to the theta, which is something that does not happen in polar coordinates, because you would have r here basically. So you don't have. So the idea is that r over L theta is just equal to dr over d theta. If you map a Cartesian grid on a elliptical grid, not only the principal direction naturally align on the principal directions you need, which is crucial, because you have the anisotropy defined in that way and you have to rotate it, but also they naturally are not distorted with a linear map, which is kind of super easy. And this equal scaling factor is also the origin of the fact that the elasticity tensor only depends on the map. because you see the modulus of the basis vector kind of, I mean, this goes away, and this does not happen in polar cloaking, which you would have at R over R, something like that, the big coordinate. And this, I mean, is not a great complication, but in this case is easier, I think, to find the map.
No, it's a really great trick. I think it's fantastic. Yeah, I really like this. Really lovely. Yeah. So please, people, I mean, maybe I'm wrong, but we still have a constant determinant of the Jacobian. So question from Zino.
In this mapping, yes, I think not.
So Zino, would you like to come forward and speak by yourself?
I mean,
Yes, give me 1 sec. Okay, he will come.
Okay. I'm not sure
Yeah, you don't need to have eccentricity for the inner and the outer boundary. Don't you have a different eccentricity for the ellipse, for the inner and the outer boundary?
It's different. It's different.
Okay.
Because you are using coordinate lines basically, and the coordinate lines here are confocal, and so confocal ellipses have.
Okay.
And it is because this boundary has not the same elasticity of this one, basically. This boundary will not have the same of this.
Sorry, Sebastian. Hello. Can you hear me?
Please come forward, Sino. Excellent.
Hello. Sorry. Thank you very much, David. Sorry for I don't have a camera. I want to ask you before you were discussing with Sebastian regarding also the from PDE paper. We want a constant Jacobian or not all the time, so it's we don't have this inhomogeneous. In the what you were discussing earlier with Sebastian, yeah, in this slide. Can you clarify this? I was a bit confused.
So
yes,
is
with regarding the elliptical or polar coordinates. Yes.
Let's start with the elliptical one. The idea is the Jacobian, let's say, is kind of the product of the eigenvectors of V, basically, for me. So what we need here is a conformal map. So when I deform this one into this one, I want not to change the ratio between lengths. So the conformal map in this case is a rigid rotation with a deformation that is isotropic. So you have just a scalar multiplied by E, the identity tensor. And so J, which is the Jacobian, is just the third power of this stretch, the change of volume, because this stretch is isotropic. So you don't actually need it to be constant in space, but you need to be like this. I mean, all in all, we can zoom in, but you can see that this cell which goes here is enlarged less than this one that goes here. But the point is, every dimension is enlarged in the same. So the ratio stays the same. The angles stay the same. So while you have designed these in Cartesian coordinates to have all these parameters to have an optimal equivalent properties, you do not lose this optimality, because basically what you're doing is just taking the cell, rotating it, and just enlarging or isotropically stretching. And what happens when you change the size of the cell is just you move a little bit frequencies that do not change the anisotropy. So the idea was to set a conformal map, so one that can be written like this. And it turns out you can do this with simply mapping linearly these four corners in Cartesian coordinates to these four corners in the elliptical grid, because of these nice properties. With the polar coordinates, it's much harder, because as you know, the length in the tangential direction does not simply depend on the variation of your coordinate, but it's just multiplied by r. So if you have the theta, which is 1 degree basically, 1 degree d theta is different here than here because you are far from R. And so because of this scaling factor, everything gets
it will shrink as you move out.
So your map, you should be it should be different to take into account for this elongation, extra elongation that you get when you go far. So all in all, maybe someone can say that this approach in elliptical coordinate has drawbacks, and of course it has, because you cannot reach perfect cloaking, but also it gives you a systematic way to deal with some problems you get when you have the non-axisymmetrical cloak. Because I mean, one problem is you have to optimize 100 cells instead of 5 basically. And if you can find a linear map, which is the easiest one, that just gives you homogeneous elastic tensor. You just have to find the hexagonal shape that implements your elasticity, and then adjust the mass locally. And it gives you really much less troubles. And the other big advantage is one single formula. You take this and stretch conformally around the cloak, and it's super easy. So of course, the drawback is perfect cloaking cannot achieve. The good thing is it allows you to not to trouble that much, considering that you have to design a whole cloak in which everything changes pointwise, basically, and not just have everything repeating on the tangential direction, basically. So this is it. And also, I think it opened up to us some interesting questions like, is it really needed, these single mode bandgaps, since we have the worst of the performance in the single mode bandgap? Maybe it's just we need if it works only below the bandgap, because just the frequency range in which work is this one. You just need the highest impedance mismatch between the fluid and the shear waves, and do not care that much. You do not care about the single mode bandgap. But maybe this needs more investigation, I think.
Really nice. I think you came up with really lovely ideas to, break down the very complex problem into manageable, simplified bits. Okay, so I would like to thank you again, Davide, for this fantastic talk. I mean, it was really amazing.
Thank you so much also for the invitation. It was a great opportunity to me. Thank you.
Bogdan, can you remind us next week who will be our next webinar speaker?
Yeah, sure. Thanks again, Davide. Really nice talk and discussions. Very interesting. Yeah, for the next week, we'll have Martin van Heek. And Martin is from the University of Cagliari in Italy. And he'll speak about metamaterials that compute. So yeah, see you guys next week.
Oh, maybe Zenon had a question, because it says I have a delay.
Oh yeah. I think I had